Welcome to Engineering Simplified. Today we'll look at what an AC waveform actually represents, what peak value means, what RMS or root mean square means, and why we use RMS instead of simply using the maximum value of the waveform. We'll then look at the mathematical relationship between RMS and peak, work through some simple calculations, and finish with a viewer test for you to try yourself. Let's start with the AC waveform. Unlike direct current, alternating current continuously changes with time. If we look at a sinusoidal waveform, the voltage begins at zero, rises to a positive maximum, falls back through zero, reaches a negative maximum, and then returns to zero. This complete pattern repeats continuously. The highest positive and negative values reached by the waveform are known as the peak values. So what exactly is peak value? Peak is simply the maximum instantaneous magnitude reached by the voltage or current waveform. For example, if an AC voltage waveform reaches a maximum of 325 volts, then its peak voltage is 325 volts. The negative half cycle may reach minus 325 volts, but when we refer to peak magnitude, we normally describe it as 325 volts. Peak values are particularly important when engineers consider things such as insulation stress, electrical clearances, short circuit forces, and the mechanical strength of electrical equipment. Now let's look at RMS. RMS stands for root mean square. RMS gives us the effective value of an alternating voltage or current. A useful way of understanding this is through heating. An RMS current flowing through a resistor produces the same average heating effect as an equivalent DC current. So, for example, an AC current of 10 amps RMS produces the same average heating effect in a resistor as 10 amps DC. This is one of the reasons RMS values are so useful in electrical engineering. When we compare RMS and peak side by side, their different purposes become much clearer. RMS represents the effective value and is commonly used for power calculations, heating effects, and equipment ratings. Peak represents the maximum instantaneous value of the waveform. Peak becomes important when we need to know the maximum electrical or mechanical stress that equipment may experience. So although RMS and peak describe the same waveform, they tell us two different things. Now let's look at the mathematical relationship between them. For a pure sinusoidal waveform, RMS voltage equals peak voltage divided by the square root of 2. And if we want to calculate peak from RMS, we multiply the RMS value by the square root of 2. The square root of 2 is approximately 1.414, so peak is approximately 1.414 times the RMS value. And RMS is approximately 0.707 times the peak value. Remember that these relationships apply specifically to a sinusoidal waveform. Other waveform shapes can have different relationships between RMS and peak. So where do engineers actually use these values? RMS values are used extensively for power calculations, heating effects, equipment ratings, energy measurements, and general electrical system analysis. When we say a supply is 230 volts AC, for example, we are normally talking about 230 volts RMS. Peak values become particularly important when considering insulation requirements, electrical stress, surge conditions, and short circuit forces. During a severe short circuit, the peak current can create enormous electrodynamic forces on cables, bus bars, and their supporting systems. This is why knowing whether a value is RMS or peak is so important. Before we move into the calculations, here are the key points so far. RMS is the effective value. Peak is the maximum instantaneous value. For a sine wave, peak equals RMS multiplied by the square root of 2. RMS is commonly associated with power, heating, and equipment ratings, while peak is particularly important when considering maximum electrical and mechanical stresses. Now let's put this into practice. In our first example, we have a sinusoidal voltage with a peak value of 325 volts. We want to calculate the RMS voltage. We use the formula RMS equals peak divided by the square root of 2. Substituting our value gives RMS equals 325 divided by the square root of 2. The square root of 2 is approximately 1.414, so 325 divided by 1.414 gives approximately 229.8 volts. Therefore, a sinusoidal waveform with a peak voltage of 325 volts has an RMS voltage of approximately 230 volts. And this explains something very important about a standard 230-volt AC supply. 230 volts is the RMS value. The actual instantaneous voltage rises to approximately positive 325 volts and falls to approximately negative 325 volts during each cycle. Now let's reverse the calculation. This time, a generator produces an RMS voltage of 230 volts. We want to calculate its peak voltage. The formula is peak equals RMS multiplied by the square root of 2. Substitute 230 volts. Peak equals 230 multiplied by 1.414. That gives approximately 325.2 volts. So a 230-volt RMS sinusoidal supply has a peak voltage of approximately 325 volts. This simple conversion appears throughout electrical engineering. Engineers may need RMS values when considering power and equipment ratings, while peak values may be required when assessing insulation, surge conditions, semiconductor stresses, or maximum electrodynamic forces. The important thing is to understand which value the calculation or equipment specification requires. Now it's your turn. An AC circuit has an RMS current of 85 amps. What is the peak current? Pause the video here if you want to work it out yourself. Remember, for a sine wave, peak equals RMS multiplied by the square root of 2. Ready? Let's work through it. We start with the formula. Peak equals RMS multiplied by the square root of 2. Our RMS current is 85 amps, so peak equals 85 multiplied by 1.414, and that gives approximately 120.2 amps. Therefore, an RMS current of 85 amps corresponds to a peak current of approximately 120.2 amps for a sinusoidal waveform. So what have we learned today? RMS, or root mean square, represents the effective value of an AC voltage or current. Peak represents the maximum instantaneous magnitude reached by the waveform. For a pure sine wave, peak equals RMS multiplied by the square root of 2, or approximately 1.414 times RMS. And to convert peak back to RMS, divide by the square root of 2. Most importantly, RMS and peak values are used for different engineering purposes. RMS is fundamental to power calculations, heating effects, and equipment ratings. Peak becomes especially important when considering maximum electrical stress, insulation requirements, and electrodynamic forces. Understanding the difference helps engineers choose the correct value for the correct calculation and ultimately design safer and more reliable electrical systems. Thanks for watching Engineering Simplified. If you found this video helpful, please like the video, leave a comment below, and subscribe to Engineering Simplified. It really helps the channel grow and allows us to keep making engineering concepts easier to understand. I'll see you in the next video.